Welcome to the fastest way to learn data structures and algorithms with this premium revision material. Today we are mastering LeetCode 207, Course Schedule. This is a classic graph problem that tests your understanding of dependency management and cycle detection, a critical skill for any software engineer. Look at the screen. We are given a total number of courses and a list of prerequisite pairs. For example, the pair 0, 1 means you must take course 1 before you can take course 0. Our task is to determine if it is possible to finish all the courses. In graph terms, we are checking if a directed acyclic graph, or DAG, can be formed. If there is even one circular dependency, finishing all courses becomes impossible. Think of unlocking levels in a massive video game. To play the boss battle, you first need to find the magic sword. But to get the sword, you might first need to complete the forest trial. This is a clear path. However, imagine if the forest trial required you to have already defeated the boss. You would be stuck in an infinite loop, unable to start any of them. Our job is to detect these logical deadlocks before the player even starts. To solve this, we use Kahn's algorithm for topological sort. First, we represent the courses as a graph using an adjacency list, and we calculate the indegree for every course. The indegree is simply the number of prerequisites a course has. Next, we take all courses with an indegree of 0, meaning they have no prerequisites, and add them to a queue. We then process the queue, completing each course and reducing the indegree of its dependent courses. If a dependent course's indegree hits 0, it is unlocked, and we add it to the queue. If we manage to finish all courses, we return true. Otherwise, a cycle exists, and we return false. Look at our courses. We have 4 courses, labeled 0 to 3. Our prerequisites are, Course 1 requires Course 0, Course 2 requires Course 1, and Course 3 requires Course 2. At the start, Course 0 has an indegree of 0. Courses 1, 2, and 3 all have an indegree of 1. We add Course 0 to our queue. We complete Course 0 and look at its dependence. Course 1's indegree drops from 1 to 0. It's now unlocked. We add Course 1 to the queue. Completing Course 1 drops Course 2's indegree to 0. Unlocked. Finally, we add Course 2 to the queue. Completing it drops Course 3's indegree to 0. We processed all 4 courses. Since our count equals the total courses, we return true. In our Python code, we first build our adjacency list and an indegree array of size n. We iterate through the prerequisites to fill these structures. Next, we initialize a queue with all courses that have an indegree of 0. We also keep a counter for how many courses we have completed. While the queue is not empty, we pop a course, increment our counter, and iterate through its neighbors in the adjacency list. For each neighbor, we decrement its indegree. If a neighbor's indegree reaches 0, we immediately append it to the queue. After the loop, we simply check if our completed course count equals the total number of courses. If they match, success. For time complexity, we visit every course and every prerequisite once. That makes it O of V plus E, where V is the number of courses and E is the number of prerequisites. For space complexity, our adjacency list and indegree array both take O of V plus E space. This is as efficient as it gets. And that is the course schedule challenge mastered. If this breakdown helped you see the logic behind the graph, hit that like button and subscribe to Leo Academy for more premium DSA guides. See you in the next one.